All right, so you've done a lot of factoring examples now after working through those worksheets from yesterday, and I asked you to group everything together into different types of factoring and just sort of try and come up with your own rules to how you could factor different types of trinomials you might run into. So, first group I want to look at are the ones that we call simple trinomials. Now, the reason we're going to call them simple trinomials are any a value that you see in the equation is going to be 1. Okay, so you'll see that's the case with a, e, r, and g. The a value for all these is 1. It's just 1x squared. If you look at n, j, and d, at first glance, none of these look like simple trinomials because they have a values that aren't 1, but all of these have various common factors you can take out. So for example, with d, you can take out a common factor of -2. With j, you can take out a common factor of 3. And once you take out that common factor, you wind up with an a value of 1. So for example, if I take out -2 out of d, I get x squared plus 2x plus 1. Okay, and you see now what's left over is just a simple trinomial. Okay, so if you look at all the ones that you factored there, you may have noticed that x squared plus 12x plus 11, let's say I did that up here, that factored into, once we did our array, we had x squared, we had 11, and we wound up with 11x and x. Okay, and one of the things we had talked about how you need to have these two numbers here multiply to your c value, 11, and add to your b value, which is 12. So you wind up with x plus 11 and x plus 1. Okay, so if you ever see simple trinomial, these are relatively simple rules you can follow. The trick is, again, finding the pair of numbers that works, but you'll see it works every single time. So here you get y, for example, I'll do r with you guys just to recap. X squared plus 6x minus 27. If you throw that into an array, we get x squared minus 27. What makes this nice and simple is that for your x squared, there's only x and x that can work on the outside of the array. So here we're looking for two numbers that multiply -27 and add to 6. So those numbers are going to be 9 and -3. So we get 9x minus 3x, which gives us x minus 3, x plus 6. Okay, so again, what you're looking for, the first thing you're always going to look for with any factoring problem is there a greatest common factor, or a GCF? And what you're looking for with a simple trinomial is two numbers that multiply to c but add to give b. So let's take a look at this example here, x squared minus 8x plus 15. Okay, so again, x and x are the only options for the outside of the array. So two numbers multiplied to positive 15 add to -8. Well, those two numbers are -5 and -3. Okay, so if I try -5 and -3, it gives me -3x and -5x. Okay, so it gives me my factored form. Okay, so that was one type of factoring that we saw. Okay, you also saw a type of factoring called perfect square trinomials. And one thing you may have noticed here, S, C, P, and O factored into these. When you had them factored, when you experimented with the arrays, you wind up with something that looked like this. You had 4x plus 3 all squared for this one. Okay, the reason we call it a perfect square trinomial is that you wind up with the same factor repeated. Okay, if you try this out with algebra tiles, you get a perfect square. So C worked out to being 2x minus 7 all squared. And maybe after a while you start to see the pattern here. You get 3x plus 1 all squared. And here you get 6x minus 5 all squared. Okay, so what kind of pattern are you looking for here? Well, if you're going to have a perfect square trinomial, you're going to have both your a value and your c value being perfect squares. Okay, so that's your first clue that you might have a perfect square trinomial. It doesn't guarantee that it's going to be a perfect square, but it's the first thing to look for. And it just means it's a nice thing to try, right? So if I see 16x squared and positive 9, I'm going to try 4x and 3. And I can try the array to see if it works out. But you'll see that some once in a while it won't work. In this particular case it does. What you're looking for here, if you do 4x times 3, that gives you 12x. If you double that, you should get the middle term. That's the other thing that will jump out at you if it is a perfect square, because in the array you're going to wind up with the exact same thing in the top right and bottom left corner, so they should add together to give you that middle term. So that's why for C, when you have 4x squared minus 28x plus 49, it's actually 2x minus 7 squared, not 2x plus 7, because the two numbers have to add to a negative. Okay, so In summary here, if you have a perfect square trinomial, potentially, if you have an a value, c value, perfect square, give this a try, see if it works, and check to make sure that your terms add up to the correct b value. If they don't, you'll have to factor it using another way. But if you do happen to recognize a perfect square pattern, it can make your life a lot easier. So let's try this one right here. 121x squared minus 198x plus 81. So if I throw this into here, 121x squared and 81. So is 121x squared a perfect square? Yes, it is. I'm going to try doing 11x and 11x. Okay, is 81 a perfect square? It is. So if it's going to be a perfect square, I can either use 9 and 9 or negative 9, negative 9. But since I need to add up to a negative b value, I'm going to try negative 9 and negative 9. Okay, and if it's going to be a perfect square trinomial, my middle term should add up to being negative 198x. Let's try that. Negative 9 times 11x is negative 99x. Okay, I get the same thing up here, 11x times negative 9. So I check, do these two add to negative 198? They do, so this is a perfect square trinomial. Okay. Okay, next type of factoring that you might have recognized, these are the ones that you noticed didn't have any b values. Okay, so it meant there was a b value of 0 in your equation. And you notice a lot of those, we also had perfect squares in there. So you had a perfect square with 16x squared, a perfect square with 1. Perfect square with 4x squared, perfect square with 9. X squared, 144, both perfect squares. L right here doesn't look like it's a perfect square, because 5 isn't a perfect square, but again, that's right here is a common factor of 5. So if I take out the common factor, I get x squared minus 1 left over, and all of a sudden I have, again, 2 perfect squares. So what you'll notice here with all of these is I have two perfect squares that are being subtracted, which is what literally means difference of squares. So difference means subtraction, so I'm subtracting perfect squares. And if you look at the final pattern here, you wound up with, for b, you had 4x minus 1, 4x plus 1. Okay, for h you had 2x minus 3, 2x plus 3. Okay, quickly you can say I is x minus 12, x plus 12. If you wonder where these values are coming from, like the x, the 12, the 2x, the 3, the 4x, the 1, they come from taking the square roots. Okay, so 16x squared. Well, what squared gives you 16x squared? 4x. What squared gives you 1? 1. And you see that 1's a minus and 1's a plus, and that's to get the middle term to cancel out to give you 0x. So our last one right here, y, for L, sorry, it's 5, and you get x minus 1, x plus 1. Okay, so if you're going to see a difference of squares pattern, one thing you're going to check, you're always going to check for greatest common factor. If you have two terms that are perfect squares that are being subtracted, you're looking at a difference of squares pattern. So I'm going to look at this example down here, 54 minus 6x squared. What I'm going to do first, I like having the x squared term written first. I'm going to have negative 6x squared plus 54. And as always, I should take out a greatest common factor. So 6 goes into both of these. I'm going to take out the negative 6, and my leading term is positive. So I'll have negative 6x squared minus 9. Okay, and just to show how this works in the array, I can put x squared and minus 9 in. So I'm going to need x and x to multiply to x squared. I need two numbers here that multiply to negative 9 and add to 0. Well, that's going to be negative 3 and positive 3. So that's what gives me the x plus 3, x minus 3 pattern. Okay, and the last type of factoring we saw were the ones that probably took us the longest to do, and those are called the complex trinomials. What makes these trinomials complex is that the a value is not going to be equal to 1. Okay, so all of these here, even after you look for any possible GCFs that might be there, you can't get around it, the a value is 1. Okay, so these are the ones that might have taken a little bit longer in the array to try and work out what's going on the outside. Sometimes the combinations of numbers you're trying to look for to fill in for the diagonals of the array can be a little bit trickier to find. So these do take some practice to getting used to. So let's just recap, for example, how k worked. So when you did k, so you put your 2x squared in the top left, your minus 5 in the bottom right. Again, what you're looking for here now are two numbers that multiply to a times c. Okay, so a times c is 2 times negative 5, so two numbers that multiply to negative 10. And these two numbers need to add to my b term, which is negative 9. So those two numbers are going to be negative 10 and 1. So that's what told me what went in my array here. So negative 10x here and 1x, or just x. And working this can be a little bit tricky, is that, with simple trinomials, the outside was very, very simple to do because I only had 1x squared. I just put x and x out here. With 2x squared, there's a couple different possibilities here. I can either have a 2x here and an x here, or I could try flipping those. Now, you'll see right here the way I have it is that's not going to work because 2 does not go into 1 easily. So 2 times some sort of fraction or decimal would be 0.5, would give me 1x. I don't want any fraction or decimals inside here. So that's not going to work. So I'm going to have to erase this and try the other combination. So depending on how complex your a and c values are, you may have to try a few different arrays out here to get it to work. But once you have one that works, for example, 2 goes into negative 10 5 times, so I have minus 5 here. X times what gives me 1x is going to be plus 1. So that's like giving my factored form of 2x plus 1, x minus 5. But you have to try a few different arrays to make that work. Okay, so let's try the one that's down here, 8x squared minus 48x plus 30. So of course I'm going to look for a greatest common factor first. So all these are divisible by 2. So I get 4x squared minus 23x plus 15. Okay, so again, I took out this GCF not only to get it fully factored, but because this is much easier to work with now. Put my 4x squared in here, my 15 down here. So I need two numbers that multiply to a times c. A times c is 4 times 15, which is 60. And these two numbers have to add to my b term, which is negative 23. So after playing around with it a little bit, you'll figure out that those two numbers are going to be negative 20 and negative 3. Okay, and this is again where might have to try a few different arrays, because your first thought might be for 4x squared to actually try doing 2x and 2x. And it might seem like it would work because 2 goes into negative 20, so you could put a nice whole number here, but 2 does not go into negative 3, not evenly. So you have to put a fraction or a decimal here, and since these are the same, both 2x, you can't flip them around. So 2x and 2x don't work. You have to try a different combination here. So the only combination you can try for 4x squared is going to be 4x and x. And even the way I've oriented them now does not work because 4 does not go into negative 3. So I have to have the 4x be over here and just the 1x there. So now I can see if it works. So x times negative 3 gives me negative 3x. 4x times minus 5 gives me minus 20x. So I wind up with 2, 4x minus 3, and x minus 5. Okay, one thing I just do want to mention here, just in terms of bad habits I often see with factoring, when you take out a greatest common factor of 2 here, that 2 does not disappear. It's still part of your factored form. If you make it disappear, all of a sudden you've lost part of your equation, and you won't have an equivalent graph anymore if you were to try and do something with this later. So that greatest common factor of 2 does not disappear, just kind of hangs around and stays in front as part of your final answer as well. Okay, so those are all the types of factoring that we've seen this year. We're going to look at some other types, some special kind of factoring coming up over the next couple days, but there's enough practice here to keep you busy. I've given you a worksheet with lots of practice with solutions on the website, and there's some neat ones here in the textbook that are a little bit different that you should definitely give a try to sort of push yourself a little bit further. Okay, that's it for now, and we'll see you in the next lesson.